Welcome to this video to finish up the notes in Chapter 10. So we need to finish this chapter talking about some of the fat-soluble vitamins. Vitamins play a very important role in cellular biology, biochemistry, the functioning of life. And so the ones that we want to focus on, and just broadly now, D, A, E, and K. So let's start here with vitamin D. Typically, one way to get vitamin D is we can actually make vitamin D from something called 7-dehydrocholesterol right here. So if we start with this molecule here, it actually is a precursor for cholesterol, but also in the skin and with the help of UV light, we can make vitamin D3, which is the main vitamin D form of vitamin D that we usually talk about. You can get vitamin D3 from milk. Milk has been, in the United States, has been fortified with vitamin D3. It's in the skin of some fatty fish, and of course some people take vitamin D supplements. But vitamin D3 is not really ready for prime time. It must be hydroxylated. One step in the liver, one step in the kidney. Again, I'm being vague about that, but that's okay. We hydroxylate vitamin D3 here at this point and this point, and then this gives us 125 dihydroxy 125 dihydroxy vitamin D3. And this is what we would call the biologically active form of vitamin D. It's involved in calcium uptake and bone development and some other things. But again, just broadly, this is vitamin D. Well, put your eyes on this, because how do we see? It all has to do with retinol. And how do we get retinol? We get it from a molecule called beta-carotene, and probably two of the more notable sources of beta-carotene are carrots and golden rice. We have an enzyme called beta-carotene 15-15' monooxygenase that converts beta-carotene to 11 retinol. And then this double bond right here in retinol is the one we're going to pay attention to. And we also need to pay attention to these two groups here. So this enzyme converts beta-carotene. It splits it up into two molecules, technically two molecules of the 11 retinol. And then the double bond between carbon 11 and 12 can be cis or trans. And when we convert the 11 cis retinol to all trans retinol, then that is the fundamental event in vision. So let's dial this back a little bit though. The retinol has an aldehyde group here. This is also in kind of an equilibrium with what we really call vitamin A1, which is called retinol. So retinol is not really ready for prime time to participate in the vision process. It is oxidized to an aldehyde, so we call that retinol. And then the double bond between carbons 11 and 12 go through a change in configuration from cis to trans. And again, that is the fundamental event in vision. But it's just not this retinol doing this. The retinol is attached to a protein called rhodopsin. And actually the retinol doesn't, in the vision process, it's not in the aldehyde form. The aldehyde part of retinol reacts with a lysine of rhodopsin to make what we call a Schiff base. Now let's explore that a little bit more. But again, don't think the retinol by itself is doing this with in the vision process. It's rhodopsin that has retinol covalently bonded to it through a Schiff base. But really what changes and when exposed to visible light is focus on carbon 11 and 12, the change in configuration from cis to trans. So let's look at this. Here's the rhodopsin shift base. So here's the retinol that we saw on the previous page. There's the aldehyde group. It is known that lysine 296 of rhodopsin. Again, this is a reaction between an aldehyde and an amine. And when you do that reaction, and I'm not going over the mechanism of this, you get what we call a Schiff base. So let's draw this out. Really, how is the retinol attached to rhodopsin to make what we're going to call the visual pigment? So here's the rest of the retinol molecule. But now the carbon of the aldehyde is involved in a double bond with the nitrogen from lysine 296. And again, this is a kind of a cartoon, so work with me here. This really here is what we call the visual pigment. The retinol attached to lysine 296 of rhodopsin via a Schiff base. Again, it's not this double bond that really undergoes change of configuration. It is the double bond between carbon 11 and 12. Again, that's the fundamental event in the vision process. So, vitamin A, very important. Beta carotene, very important in our diet. All right, well, let's just, again, we're giving the kind of the big picture here. So let's see what we have next. We have vitamin E, and we have vitamin K. Again, we're talking about the fat-soluble, lipid-soluble vitamins. Vitamin E is probably best known as an antioxidant. It is a free radical scavenger. We will talk about this molecule later on in this class. There's many sources of vitamin E in our diet. If you look it up, it's just very, very long list. It has been in the news lately because of a form of vitamin E called vitamin E acetate. And so I think you should know what that means. So here's the structure of vitamin E. Now vitamin E and vitamin K have these 5 carbon units called isoprene units. And this is actually a somewhat common structural feature in certain biological molecules. So isoprene is this, and then it's used in many biosynthetic reactions to make molecules like vitamin E and vitamin K. So if you see a kind of a repeating 5 carbon intermediate, then you see, or you can know that, oh, that came from an isoprene unit. And interestingly, isoprene in industry is used to make a variety of tires. So anyway, well, back to vitamin E real quick. Vitamin E acetate has been found to be in the vaping oils, the vaping liquids, has really been identified as the major culprit for lung damage. And so what's the difference between vitamin E and vitamin E acetate? Well, I'm going to point your attention to this red dot with the oxygen. That oxygen, it's an OH group in vitamin E, but if you add an acetyl group to that, you get vitamin E acetate. Again, in the news in terms of the problems with vaping. Vitamin K. Where are you going to get your vitamin K? Well, do you like kale? Do you like collard greens? Do you like turnip greens? The greens are kind of the major source of vitamin K in one's diet. Again, its structure here has kind of a it's kind of constructed from these isoprene units, obviously these 5 carbon repeating units are what make these 2 molecules fat soluble. This makes them very hydrophobic, right? Very nonpolar. Well, vitamin K is involved in blood clotting, and it is what's called kind of a phyloquinone. Here's kind of a quinone ring right there. And what we're going to find out on the next page is that, you know, how exactly is vitamin K involved in blood clotting? I think it's important for you to know that. And vitamin K undergoes, this quinone type ring, undergoes redox cycling in the blood clotting process. So let's talk about that, because that sounds interesting. All right. Well, there are a lot, let me dial that back. There are several proteins involved in blood clotting. For example, we have all these blood clotting factors. If you take pharmacology, we get into this in much greater detail. I'm going to give you the kind of the 40,000-foot view. There are certain glutamic acid residues in molecules involved in blood clotting, like prothrombin, plus these are called blood clotting factors. These are proteins, and in fact you'll learn that they're actually serine proteases later on if you take pharmacology. Factors, blood clotting factor 7, 9, and 10 all have certain glutamic acid residues that undergo a post-translational modification. They get an extra carboxyl group. So here we have glutamic acid from these proteins. There's an enzyme called gamma-glutamyl carboxylase. And again, I'm not going over the detailed mechanism of this, but look, these particular glutamic acids get 2 carboxylate groups now. And so we call this gamma-carboxyl glutamic acid. And without going into any detail, gamma-carboxyl glutamic acid residues are involved in the process of blood clotting or blood coagulation. Now, what we know is that this post-translational modification of glutamic acids requires vitamin K hydroquinone, right here, going to vitamin K epoxide. Well, this is a redox. In fact, the carboxylation of glutamic acid is redox, and it is a reduction reaction overall. Okay, it requires carbon dioxide, it requires molecular oxygen. Again, a detailed mechanism I don't want to get into, but it's a 2-electron process, and so that ultimately becomes is a reduction issue. So vitamin K hydroquinone needs to go from the reduced form to its oxidized form. And I've shown you the structures here. Vitamin K hydroquinone is called KH2, and it has 2 hydroxyl groups in these positions. Here's the rest of the vitamin K molecule. I don't care about that. It just makes it fat soluble. It's not involved in the redox chemistry at all. So when glutamic acid side chain goes to gamma carboxy glutamic acid side chain, then KH2 goes to KO, which is vitamin K epoxide, and it is in the oxidized form. And I've drawn the structure for you over here. Well, to continue to carboxylate glutamic acid side chains, we have to recycle vitamin K epoxide back to vitamin K hydroquinone. And an enzyme called vitamin K epoxide reductase, quinone reductase, is involved in that. So now we know the biological role of vitamin K. It undergoes redox cycling. And it's involved in the carboxylation of certain glutamic acid residues and proteins involved in blood clotting. And so this redox cycling is important for us to continue to carboxylate glutamic acid side chains. Now, that's the biological role of vitamin K, and actually inhibiting redox cycling of vitamin K is a drug target, because this enzyme, this vitamin K epoxide reductase enzyme, actually is inhibited by a molecule you may have heard of called warfarin. Warfarin. It is a blood thinner. It is an anticoagulant, because if you, let me write this out here. If warfarin inhibits this enzyme, this vitamin K epoxide reductase, or it's called a quinone reductase as well, then you stop redox cycling of vitamin K, then you stop the gamma carboxylation of glutamic acids in these blood clotting factors, and then you basically work against blood clotting or blood coagulation. So it's definitely a blood thinner. It's also called Coumadin. Is one of the brand names, or the kind of technical name for it when it's sold. You may see some commercials about warfarin on TV. I think in class I may show you a video of something called Eliquis. Eliquis is a newer type of blood thinner that just attacks one of these blood clotting factors, not all the ones listed above. It just attacks or inhibits factor 10A, or if you want to call it, it's Roman numeral 10 with this X. Another fun fact, as I kind of end up this, if you actually get rat poison, it's warfarin. So people basically use it in somewhat higher doses. It's a very rodenticide. It can kill rodents. And so for us though, if you take too much of it, it would certainly kill us. But at the right dose, it's a very powerful and widely used, warfarin is powerful, widely used blood thinner. All right, that's chapter 10. And I think that's it. Thank you.